Thank you very much, Bill. Yeah, I'm a bit worried because a lot of my slides have equations in them, and I seem to be the first one doing that, but I'm sure I won't be the last one these days. But just see if it works or not. I'm curious. We're going to have a little game between Laplace and Boussinesq, and if you read the title, you know that Laplace will actually win. It started here in a project of Tamo in Rwanda, where farmers are farming the valley bottoms here. And what they do is they build these raised beds, and the authorities didn't like those things so much because you see they're very narrow, a lot of water in between, and the authorities said, no, that's a waste of space, you have to make these things wider, why don't you make them wider? And of course we started looking into those things. We did some trials actually. And you see here we made a narrow bed and a very wide bed to see if there were any differences. We did some discharge measurements, and actually I never used them later on, but still we had them. And I even checked if the soil was perfectly homogeneous and isotropic, and it was. I also put this picture in, so for those of you who don't recognize me, this is about 20 years ago or so. So some people did not recognize me today, and I look carefully, I don't understand why, but I think I had a slightly longer nose those days. Anyway, so in Rwanda I had to wait a lot as well. So while I was waiting for stuff to arrive, I started thinking about, what is the theory? And this would be more or less the sketch in 2D. They were pretty long, so we can go in 2D. So you have some water here, some water there. There's an impermeable layer at the bottom, because that's actually why that sort of determines the height of these beds as well. The farmers sort of harvest some soils to make these beds, and they cannot go much lower. We know that Laplace will work in that, but most of these drainage formulas, they are based on some form of the Boussinesq equation like you see here. And the question is, because Boussinesq is based on the assumption that vertical movement is negligible with respect to horizontal movement, you cannot really say that when you have these really narrow beds. So is that true? This was more or less the question. And this Mr. Charnier here had a solution for flow through a dam, and there he said it doesn't matter. For steady state, flow through a dam, there's a discharge through a dam, Boussinesq and Laplace give the same results. But I thought, well, does it still hold for what happens to the groundwater level and what happens in non-stationary situations? And well, I stared at it a lot. I remember Jan Bol sending me, going to the library here and sending photocopies and things like that. But while in Rwanda, I couldn't figure it out. So, well, what do you do then? You go to Yves. And Yves said, okay, that sounds interesting. Let me look at it. And within no time, of course, he came with a solution, and he was a bit upset. I'll come to that in a little bit. But I'll try to get you through this, the way this can be solved, this problem. First, we have Laplace in 2D, and then you can notice that any combination of these functions, or a sum of these functions, are already a solution to the Laplace equation. So we have quite some space to work with. If you take twice the derivative to x, it has to be the minus of what you get if you take twice the derivative to y, and all these things work. Then if you look at the boundary conditions of this problem, it's also quite, some of them are nice, like this one, for example. This is just hydrostatic, so we have a given potential. Sorry, I use phi for potential. We did that all the time. It's not usual, I believe, but okay, that's what we did. And here you have a no-flow boundary, so you have the derivative must go to 0. And the nasty one, of course, are the boundary conditions on this free boundary, because you don't even know where the boundary is, and that's sort of like problematic. And here you see a linearized version of the dynamic boundary condition here, and it's actually a much nastier one. So you have to solve your partial differential equation, you have another partial differential equation as your boundary condition. And because you don't know where the boundary is, you also have a second boundary condition, and that is that the potential is equal to the height in this case. And the height, we all measure everything with respect to y equals 0. So that's the problem. And then Yves said, well, why don't you use this as a, no, he basically saw this, I think, as a solution to the problem. And you see this, we linearize with respect to this h0 here, and we say, well, the changes with respect to that are relatively small. And then we have this series, this infinite series of a sine times a hyperbolic cosine, and times a constant. Actually, it's not a constant, it's a time-dependent function this time. And when you look at it, you know, of all these combinations, it is a fortunate one, because if x equals 0, then this indeed goes to 0, and we get h0. If x equals L, sine also goes to 0, and we're back here again. And if you take the derivative with respect to y, you get the hyperbolic sine, and when you fill in y equals 0, you get 0 there. So all these already are done, and also Laplace is done. So all we have to do is worry about the nasty one there on top. And well, this is the same equation. It's important that we did linearize, or linearized, and basically what we say is, okay, the groundwater level eta is equal to this level in the ditches plus a little bit. And when we can do that, when it's a valid approximation, we come then to the next set of equations, and we said, okay, then you can write for the groundwater level, you can write this solution, and you see the difference is because at the upper boundary y equals h0, this is sort of becomes now the equation that you have. And what you have basically, because this is now a constant, these are all except for the n of course, you have a Fourier series more or less. So you have something that you multiply with sinuses, and that you use to find these groundwater, and that's what we want. If you fill this one in the dynamic boundary condition for the groundwater level, for the potential, then you get for each epsilons, for each of these functions, you find a differential equation that looks like this. And I'm cutting a few corners here left and right, but it's basically what it is. This is a relatively simple differential equation, except that you have it for every term in your Fourier series. Now, Kirkham already gave this solution, except he didn't have a time-dependent function. He just had the fixed solution, and he used it for steady-state solutions. And so I asked, he's like, how do you know that this will work? Yeah, that you can just multiply, you know, that you can make all these things independent of each other. And he says, well, you don't, but you would be stupid not to try. And that was, for me, was an important learning moment again, because you know, I didn't know you were allowed to try things when you do math and stuff like that, so I had to learn that. When you then solve it, basically we have the whole solution, and it's actually, we developed a very general solution with based on Green's functions and stuff like that. That's in the paper. It's a bit elaborate, and it wouldn't fit so well on the screen. So this is for particular cases, it becomes a little bit more manageable. And this is one, for example, for streamlines after the bed has come into some kind of equilibrium, and you stop, and then you get this solution for this. And it's you know, you also immediately see why Kirkham, for example, didn't bother. I mean, he may have seen this possible as a possible solution, but you can only do that when you have computers. And that was sort of, in the early 90s was the first time we sort of had reasonable access maybe to these kind of computers. And the nice thing, of course, and that's why it's already 1-0 for Laplace, while Boussinesq is not even in the field yet, but it's because we have streamlines, and that's of course something you will never get with Boussinesq. Now, so it's very general. Any kind of boundary condition on here, any initial condition you can fit, as long as you can fit a Fourier series on it, which most decent functions you can do. Like I said, for very general equations, it all works fine, but also for every specific case, of course, it works. This is a classic case, I would say. You start out with maybe water that's completely in equilibrium, and then all of a sudden you drop the water here, so you get a sort of a sudden drawdown, as it's called. Or alternatively, what they say, you have a sort of an impulse input at t is 0, all of a sudden you have a lot of water, and whatever happens here, we always forget about it. I think it's you know, it's sort of like an artificial thing, but it's of course from a systems point of view, it's very interesting to know what the impulse response is anyway. So for this one, when you fill in the general equation, these are the solutions. And you can actually, in a very parallel way, do the very same for Boussinesq. Now we're looking at the discharge, actually. And when you compare them one-on-one, you see that they're almost the same. Yeah? Except for wherever there's a hyperbolic tangent here with an argument, here you just get the argument. So everything maps one-on-one, this, except here there's a hyperbolic tangent with an argument, and here's just the argument. So it's kind of interesting because this of course is not the same as this in general. So that was a bit of a shock to Eve. I wasn't so shocked because for me it was more the shock to see all the math on the paper. But basically, he said, yeah, I checked it twice. Please check again. And of course there was no error in there. And you can see what's happening. It's kind of interesting. To me, that was actually why I like this solution a lot, is because it really, it shows you that the physics that go in are the same physics that come out in the end, and I'll try and explain it. If you look at large times, then only these Fourier series, only the first term dominates. And then what you get then is this, so you don't have these infinite sums anymore. For large times, this is the comparison. And it's of course still the same, but it's almost the same, except for, again, this thing. And what happens is when you look at the Taylor expansion of a hyperbolic tangent, it looks like this. So yes, if x is small, then actually this is true. Yeah, so if your argument of x is small, then it works. And this is actually where Eve got really a bit scared, because the hyperbolic tangent is never larger than 1, and here's pi. So he said, okay, of course there's a difference between Boussinesq and Laplace, but how can it be pi? How can it be that large? And I must say, because what he does, what I would never dare to do, but he, wasn't too worried about it. All these things were going to 1. So we had a saturated hydraulic conductivity of 1, drainable porosity of 1, everything was 1, because later on you just put them in, so why bother with all these things? And that fits them, because then you have a pi here over, this is 1, this is 1, all of a sudden there's more pi there. That was a bit scary, because why had nobody ever noticed this? And then when you go back and look at, put all the things back in, then it all fits it all of a sudden again. And it shows very nicely, and for me that was a nice aha moment, like, okay, if your vertical dimensions are negligible with respect to your horizontal dimensions, this is the distance between the drains, this is the depth of the drain. If that works, then the whole thing works again, because then this holds and you can forget about all these higher order terms. 1, maybe. Then you can do the same thing, then you can ask, how about for short times? And these diagrams you may have seen, this is dq dt versus q. So it basically gives you the slopes, gives you then the basic the differential equation, and these are at log scale, these are dimensionless number. And then you see for the Boussinesq, people have shown that it's like, okay, you have a slope of 3 for early times. By the way, the early times are here with large q. They go down, and after a while you get this slope of 1. So here you basically, q goes down with the square root of time, and after a while you get a nice linear reservoir. And people have used that for analytical purposes. If, however, you do Laplace, it turns out, which should be the more complete equation. When you do this for Laplace, you see actually this, yes, you have 1, yes, you have a slope of 3, but then you go up to a slope of 7. And when you keep doing that, for very short times, you will go to infinity actually. So if you do this analysis with using these different slopes in dq dt analysis, you have to make sure that you are somewhere in the domain that it's valid, and you cannot just apply it blindly. And to me, again, it makes a lot of sense, because what you're doing in this with this impulse response, you have you build sort of a mountain of water, and then you say go, and then also, of course, if t is 0, a lot of the water is actually moving down. So you can, again, not automatically neglect the fact that there's downward movement with respect to the vertical movement. And for those who are counting, so the final result is Laplace is 3, because you have streamlines. It works for any geometry and also for short times. But of course, most of the time, 99% of the time, it's okay to use Bouginess, but we now have a way of checking things.
Perfect.
Yeah.